The previous video in this playlist introduced the Python package Pulp. Let's look at a more complex problem. Let's assume you run a company that has customers in 5 countries, say the UK, France, China, Japan, and India. Each market has a minimum level of demand, denoted DJ, where J runs from 1 to 5, capturing the 5 countries. The company owns a factory in the UK which can produce all the output required for all markets. However, transportation costs and customs regulations make the delivery from the UK to all markets costly. The company can start another factory, say in India. Note that you can continue operations in the UK at no additional costs. The key question to answer is, how much are you willing to invest in India? So we have 2 different cases. We have our base case where we only have 1 factory in the UK and deliver to all other markets. And then we have an option of a second factory. And for the second factory, we have to think about optimizing our routes. So it's basically about route optimization using Pulp, which is a classic application. Demand in each country defines the minimum level that must be delivered. Without any optimization, we can calculate the total delivery costs in the case without outsourcing. The second case, where we outsource, we have to think about optimizing it. So we optimize the routes that minimize total delivery costs. To formalize this problem, we start by importing Pulp. You see here our import statement. And then we define a list containing the locations of factories and markets. The dictionary called demand defines the minimum deliveries for each market. The array called delivery provides delivery costs between factories and markets. So for instance, if we look at the number 1, this would be a UK delivery. Moving on to the next cell, this would be a UK delivery to France, then UK to China, and so on, Japan, India. And the second row is for the factory based in India. Pulp offers the makeDict function, which we see in use here. It just simplifies putting the information into a dictionary. The dictionary uses a list, a factor market pair as keys. A print statement checks the structure of the dictionary in line 34. Next, we create an instance called model of the LP problem class, which refers to a minimization problem by default. Using list comprehension, we create a list of tuples for all factory market pairs called routes. Finally, we define variables based on the routes using the LP variable.dicts function. We regard the demand as the minimum delivery requirement. Accordingly, we set 0 as the lower bound and do not specify an upper bound. Furthermore, we assume that deliveries are in whole quantities. So we are working with integers, and you see that specified here. Next, we add the objective function, which refers to the sum of delivery costs based on all possible routes. The LP sum function is applied to a list. The list in turn is created from a list comprehension operation. Each quantity delivered from a factory to a market is multiplied by the associated cost using the factory market key in our dictionary. We describe the objective function as the sum of delivery costs with outsourcing. Next, we add constraints based on the minimum deliveries required for each market. Deliveries can be fulfilled from the UK or India, hence we have to add both locations using list comprehension and the LP-sum function. After specifying the outsourcing problem, we apply the solve method to the model and print solutions. Using the var_value attribute, we access optimal values for each variable, which captures delivery quantities between each factory and market. Finally, the value method is applied to the objective function to display the total delivery costs in the case of outsourcing. In summary, the model provides an optimal route selection, minimizing delivery costs when we operate factories in the UK and India. To decide the maximum level we can invest in India, we derive delivery costs without outsourcing production. From the costs dictionary, we select all routes starting in the UK and add delivery costs for each market. Finally, the cost difference estimates the benefit of outsourcing, which is the upper bound that we might be willing to invest. Let's just run our script. As always, GitHub provides access to all the code. You find a link in the description. You also find a link to our new book on business analytics using Python, which should be out hopefully in January 2025. And this is part of one of our chapters. And here we go, it's all optimizing our routes. And so we see how the delivery will happen. So if you have the outsourced option, China will be served from the factory based in India, the same with Japan and the Indian market. And the other markets will be served from the UK. And you can calculate the costs and you can compare the costs, and you then obtain an estimate for the upper level that you're willing to invest. Now this video is a nice demonstration of the use of Pulp to solve optimization problems in the context of managing production and deliveries, route optimization, and so on. In many settings, however, we do not have all the information needed to formalize an optimization problem. In these cases, simulated data might be required to model different choices. Great, I see you in the next video.